Hello everyone, welcome back to this channel. So we are doing Kaggle Learn, and as of now we have done this lesson, a single neuron on deep neural networks. Okay, so we did the tutorial and the exercise part. Let me revise. First we learned what is a linear unit, like uh, a neuron, a simple neuron we can say. W is the weight and B is the bias. X is the input. Y is the output, right? So we understood how we can give multiple inputs as well. Like here W0, W1, W2, all of them are weights. B is the bias and these are inputs and we are predicting the output. Okay. And also we did the exercise where we created this simple single neuron, right? Next we studied about deep neural networks. In deep neural networks, we have created layers, like not a single neuron anymore. You have dense layer, you have input layer. And also we studied about the activation function. There are different type of activation functions by which we can capture the non-linearity from the data, right? And it may be sigmoid, maybe ReLU, maybe 10H, but we also saw that mainly ReLU is used because it gives a good performance. But all other activation functions can be used also depending on your input type. Okay. And see here we have used ReLU function on single neuron. Then we have used stacked dense layer. This is a layer, input layer, two hidden layers, one output layer. Okay, so this is a stacking dense layer, and in every layer you have used a ReLU function. This is the graph of ReLU we studied, right? Okay. Next, we understood how we can create a stack dense layer. Okay, like what is the input shape and define a model with hidden layers. These inside layers are hidden layers. This is the input layer because you are providing the input shape. This is a hidden layer. Sorry, this one is a hidden layer. This is also a hidden layer, and the last one is the output layer. Okay, so we have defined a model with hidden layers. Now, activation layer, they also asked that create some different activation layers. Don't include them in the hidden layer. So, what we did here, we created a different activation layer and a different dense layer. Okay, so all these things we have done. And also, we saw how ReLU looks and how different categories of ReLU like ELU, CELU, how this activation function looks like. Now, today we are going to understand stochastic gradient descent. Okay. First, as usual, we will read the tutorial, then we will do the exercise. Okay. Now, first, let me read this thing. In the first two lessons, we learned how to build fully connected network out of stacks or dense layer. When first created, all of the network's weights are set randomly. The network doesn't know anything yet. In this lesson, we are going to see how to train a neural network. We have just created the setup, but we have not trained the model yet. Okay, we have not started the training part. That's what we are going to learn here. How to train. We have created the model. Now, how to train. Okay, as with all machine learning tasks, we begin with a set of training data. Okay, each example in the training data consists of some inputs together with an expected output. Simple. Training the network means adjusting its weights, right? What we learned that W0, W1, these are weights. So our job is to adjust the weight so that we get the desired output. So that in such a way that it can transform the features into the target. Okay. Now suppose they have given an example. In the 80 cereals dataset, we want a network that can take each cereal's content and produce a prediction for that cereal's calories. Suppose you take any cereals, there are some sugar, some amount of fiber, some amount of protein. So you can calculate depending on this that how much calories the cereal. Okay. So if we can successfully train a network to do that, its weights must be represented in some way that the relationship between those features and that target as expressed in the training data. Can you tell me what do you mean by features and what do you mean by target? Simple concept, just to what features mean here: sugar, fiber, protein. How much of sugar, how much of fiber, how much of protein you are providing. And what is the target? Target means the output variable. What is the calories? Okay, so input is features, target is the output. Simple things. Anyway, in addition to the training data, we need two more things, a loss function and optimizer. Okay, so what we have done, we have just created the model. What is our job now? Our job is to train the model. And what do you want to achieve by training the model? Simple question. We just want to calculate the target, like calculating the calories. Okay, now how we can train the model? For that, we need a loss function and an optimizer. What is a loss function? Loss function mean Loss function means that you measure how good the network's prediction are. Okay, you have applied your model, you are predicting something. But the real output may be something else. So how close you are to the real output, how much you are guessing correct, that is what you have to be concerned about. So a loss function provides you that how much good you are, how close you are, or we can see that how much difference you have from the real output. So by using these loss function, you can improve your model. And optimizer means that how to change its weights. Sugar has its own weight, fiber has, protein has. So you can change its weight so that you can predict almost correct. Okay. So improving these weights or changing these weights is called an optimizer. Fine. So we need loss function, we need optimizer. Now let's dive deep. The loss function means we have seen how to design an architecture for a network, but we have not seen how to tell a network what problem to solve. The loss function measures the disparity between the target's true value and the value model predicts. We have just discussed different problems call for different loss functions. Suppose we are working with regression problem where you have to predict a numerical value, or suppose you are working with some categorical functions where you have to predict the category. So depending on that, your loss function will differ. There is no single loss function. For every model, the loss function is different. Okay. So where the task is to predict some numerical values like 50 cereals category or rating in red wine quality. So other regression task might be predicting the price of a house or fuel efficiency of a car, where you are just calculating a numerical value. That means you are working with regression problem. So depending on whether it is a regression problem or whether it is a classification problem, or depending on which kind of model you are using, your loss function will change. Okay. Now common loss function, we will discuss about a common loss function for regression problem, that is MAE. MAE means mean absolute error. For each prediction, MAE measures the disparity from the true target by an absolute difference. I have just said that your calculating value, this is the your prediction value. Sorry, model has predicted this value, and y true means this value is the real value. What has happened in reality. So if you calculate the difference, you will be understand that how much different your prediction is from the true value. This is what is known as mean absolute error. Okay, this is the straight line like y equal to wx plus b. Okay, this you have calculated. So point on this you have predicted, but these scattered points are the real points, the real target value. But you have calculated that your target value is lying on this line wx plus v. Now what happens? You have calculated this one. Your model has predicted this one, but the real value is this one. This is the difference. Same, you have calculated this one, but real is this one. So this is the difference. Here, difference is almost null. Same, but here also you have your model has predicted this one, but this is the real one. So there is a difference. There is a difference. There is a difference. There is a difference. So if you add all of these differences you found, then this is known as mean absolute error. You are just calculating the absolute error. Okay. So all you have to remember that this is a common loss function used for regression problems, and this is calculated by this way, a true value minus the predicted value. So here they have also calculated what is the value of mean absolute error. Anyway, beside MAE, other loss functions you might see for regression problems are the mean squared error. Mean squared error is also simple. You are just square this value. Anyway, different type of loss function can be calculated. Okay. During training, the model will use the loss function as a guide for finding the correct value of its weights. Lower loss is better. Obviously, we are looking so that the loss is less. If the loss is less, that means the points are very nearer or it is lying on the line. That means your model is predicting correct. That is what your target is, that predicting as correct as possible. So your job is to minimize the loss function. That's what your target is. Simple thing. Anyway, the model will use the loss function as a guide for finding the correct value. In other words, loss function tells the network its objective. Okay. Optimizer stochastic gradient descent. We have described the problem we want the network to solve. But how to solve it? This is the job of the optimizer. Okay. So first we have created the network. Second, we have told that please minimize my loss. Now, how will the model do? We have to tell how will it do. Okay. But for that we need optimizer. Virtually all of the optimization algorithms used in deep learning belong to a family called stochastic gradient descent. They are iterative algorithms that train a network in steps. How? One step of training goes like this: sample some training data, run it through the network to make predictions. Okay, just take some data by sampling. I hope you know what is sampling. It means that you are just selecting some from the population. You have 100 people, but you are taking 3 people. That is what is sampling. So you are taking some training data from the complete data set. Okay, and run it through the network to make predictions. That means you are just making the predictions. Now you have predicted. Now what you do? Second work is measure the loss between the prediction and true values. You have predicted, you have true values. So now you just calculate the difference, mean absolute error or mean squared error or any other kind of loss. So then once you calculate, you have the loss. Now what you have to do? Adjust the weights so that the loss becomes smaller. Okay, so either you have to increase the weight or you have to decrease the weight. You have to check for which uh, side the loss is the minimum. So you get my point. First, you have to take some training data set. You have to make the predictions. Then you have to make the then you have to calculate the loss, and then you have to adjust the weight. W1, W2, W3 we have studied before. You have to adjust the weight so that calculated loss becomes smaller. Okay, then just do this over and over until the loss is as small as you like. It will not be zero, but our job is to make it near zero. As much as possible, we will try to make it small. Okay. See, now let's read this. Each iteration sample of training data is called a mini batch. Simple thing that when you are taking some sampling from the training data and you are trying to calculate this fitted line, that is known as mini batch or we can say batch. But a complete round of the training data. I mean, if your training data has 1,000 points, let's say, then you are taking all the values, you are working on all the values, the complete round, that is known as epoch is going to be used a lot. So you understand the difference, that mini batch means each iterations sample of training data, but when the complete round is taking, when you are going through the complete data set, that is known as epoch. The number of epochs you train is how many times the network will see each training example. That means if you give 10 epochs, that means the model will see the training examples, the data points 10 times. If you give 20 epoch, then it will be trained for 20 times. That means the network will see any particular data set 20 times. Okay. Now the animation shows the linear model from lesson 1 being trained with SGD. The pale red dots depict the entire data set. See this one, which are pale, these are entire data set. While the solid red dots, while the solid red dots are mini batches. Every time SGD sees a new batch, it will shift the weights. So whenever it will see a new batch, it will shift the weight. Weight means the W and the B. B is the intercept, the Y intercept, and W is the weights towards their correct values on the match. Batch after batch, the line eventually converges to its best fit. You can see that first it is starting from here. See now slowly it is trying to converge. Once it minimizes its loss, see here. Now it has started like this, but it is in every batch it is improving its words, and finally this is converging with the data set. So once you calculate this one, now you can see that your loss will be minimum, and that is what your main target is. Okay. You can see the loss gets smaller as the words get closer to the true values. Fine. Next one is learning rate and batch size. Notice that line only makes a small shift in the direction of each batch. The size of this shift is determined by learning rate. See here, this is taking a small shift. This is what is known as learning rate. Learning rate we can change. Smaller learning rate means the network needs to see more mini batches before its weights converges to their best values. That means the rate at which it is learning, and you can also modify the learning rate by multiplying it with some smaller number or bigger number the way you want. That means how quick you are learning. In every batch, it is improving its weights. That is what is called learning rate. Simple concept. The learning rate and the size of the mini batches are the two parameters that have the largest effect on how SGD training proceeds. The iteration is often subtle, and the right choice for this parameter is not always obvious. Anyway, fortunately, for most work, it won't be necessary to do an extensive hyperparameter search to get satisfactory result. Adam is an optimizer that has adaptive learning rate that makes it suitable for most problems without any parameter tuning. See, there are different kind of optimizer. They have talked about one optimizer, that is Adam. Simply that there is not a single one. You have different kind of activation function, you have different kind of loss function, you have different kind of optimizer function. Depending on which type of data set you are working, you have to understand that which one will be better for you. Sometimes you have to work with more than one, and you have to try to predict that which one is giving you the best result. Okay, it's not that only one optimizer is there, Adam. Here they have talked about one optimizer. Anyway, after defining a model, you can add a loss function and optimizer with models compile method. Okay, so you have to write model dot compile optimizer equal to Adam, loss equal to MAE. Simple things. Notice that we are able to specify the loss and optimizer with just a string. You can also access this directly through Keras. Keras, you know that deep learning library. What's in name? The gradient is a vector that tells us in what direction the weight needs to go. More precisely, it tells us how to change the weights to make the loss change fastest. We call our progress gradient descent because it uses the gradient to descend the loss curve towards the minimum. Because we are trying to minimize the loss. So, suppose this is the loss curve. So, we are just trying to go in the that point where the loss is the minimum. That is why we are using gradient descent word. Stochastic means determined by chance. Okay, our training is stochastic because mini batches are random samples from the dataset. You are just taking some random samples and you are trying to minimize the loss. So this is kind of sampling, like you are taking a chance. And that's why it is called stochastic gradient descent. They have just explained why the name is like that. Example, red wine quality. Now we know everything we need to start training deep learning models. Very good. Now the data set consists of physiochemical measurements about 1600 Portuguese red wines. This was in our first lesson. I hope you remember these are the components we have, and the target is the quality. So you can say that these are the features, inputs, and this is the output, that is the target. Fine. Also included is a quality rating for each wine. How we have to predict the quality from these measurements. We have put all of data preparation into this next hidden cell. It's not essential to what follows. So feel free to skip it. One thing you might note for now though is that we have rescaled each value to interval 0 to 1. Okay. Here they want to say that they have scaled the value. Some values are scaled here. How many inputs should this network have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. See, extend dot sub 11, and these are the number of rows, complete data set. We can discover by looking at number columns. Be sure not to include target. Target is the quality. Fine. 11 column means 11 inputs. So we have chosen a 3-layer network. We did this in our last class. 3-layer network means that there will be one input layer, two hidden layer, and one output layer. Okay. These networks should be capable of learning fairly complex relationships. Fine, see here they have taken dense layer, 512 input, 512 neurons, 11 inputs, and the activation function they have taken ReLU. In the second layer, in the third layer, they have used same activations, and one output. Okay. These things we did in our last class. Deciding the architecture of your model, you should be part of the process. Start simple and use validation loss. You have to now calculate the loss. 3 step, creating the architecture. First step is done. Second step, you have to calculate the loss. Fine. After defining the model, we compile the optimizer and the loss function. They have used Adam optimizer, and the loss function is MA. Sorry, error. Just vibrate minus y real, or y real minus vibrate. Now we are ready to start the training. We have told Keras to feed the optimizer 256 rows of the training data at a time. That is the batch size. Batch size means some sampling data. So you are taking 250 rows at a single time. And after one batch, your weights will be optimized. Like it will be changed so that the loss becomes smaller. Okay. And you do that for 10 times in the complete data set. That is what is known as epochs. So in each batch you will take 256 rows and do this for 10 times all the way through the data set. Fine. See, they have done. How to do this? History means they have just kept the total historical data in the history. So model.fit, I think if you have learned, you know that whenever you train any model, you have to call this fit function. And extend means the training data set. You have complete data set of 1000 points. Suppose 800 each for training, 200 each for testing. So in 800 data points, you have extend and widen. Extend means the input feature, widen means the output. Okay. So you have just taken the training data set. You have removed the testing data set because testing is not for training, right? So you have taken the training data set, and in your data set you have some training inputs, and widen means the output. Okay. Now what is the validation data? X valid, comma Y valid. What is the batch size? They have told that in every batch you take 256 rows. So batch size equal to 256, and do that 10 times all the way through the dataset. So epochs is okay. Now see here. In epoch 1, in the first epoch, you have 10 epochs. So they have done 10 epochs, and in each epoch in one, they have trained the model. And after training the model, this is the loss. See, after every training, or what is your third step? So now our job is to, after every training, you have to minimize the loss. So the model gets optimized. See, 0.24, 0.13, 0.1181, 1117, 1010, then it has become 0.1005, 1011. It's almost same. That means the model has reached its position. So now your loss is minimum, and you can see that your epochs has also been completed. Okay. Now you can see that Keras will keep you updated on the loss as the model trains. Often a better way to view the loss is by plotting it. That means if you plot it, you can understand what how your loss is getting reduced. Okay. Now see how to plot this. So history DF, that means we have kept this in history. So we are just taking this history dot history and you are creating a data frame because this is the training history. So you have to convert this training history into a data frame and then from the data frame you can plot the loss. See, this is the loss. It was bigger before, then it has decreased after every epoch. So after first epoch, it has decreased so much because for the first time your model has trained, so obviously it will decrease much more. Then also it has decreased. After fourth epoch also decreased. After six, after eight, and then it has become almost normal. That means you have decreased your losses. Okay. So you created your network, you applied a loss function, you applied an optimizer, and you have reached here. Okay. So notice how these levels of as epochs go by, loss curves become horizontal like that. It means the model has learned all it can, and there would be no reason to continue for additional epochs. Okay, fine. Now let's do the exercise. See, in this exercise, you will train a neural network on the fuel economy dataset and then explore the effect of the learning rate and batch size. Okay, just let me run this first because this is setting up the plot. It is important. Here we have downloaded all the necessary libraries. This is the data set and the data set is about uh, fuel economy dataset. Cell to define the network we will use for this task. TensorFlow, Keras you have downloaded and layers so that you can create the model dot Keras dot sequential and you can calculate the model. So layers dot dense 128, that means you are taking 128 nodes. What is the activation function? ReLU input step means whatever the input step is provided from here. They have also already given the inputs. Now see, now our job is to, before training the network, we need to define the loss and the optimizer. So you have to use the model compile method. And they have also told you that you have to use the Adam optimizer and the MAE loss. MAE means mean absolute error. What type of losses we have studied right now? Mean absolute error and mean standard error. Though there are different types of losses. Okay. Okay. Now let's do this. Before training the network, you have to define the loss and the optimizer. So using the models compile method. So I can write model.compile method. Here I can provide optimizer. Optimizer here is Adam and what is the loss function? Loss equal to MA. You can give other losses as well. Okay, fine. Now let's run it. Fine. If you want, you just can. First, if you can't, first check the hint. See model.compile. Inside this, you have to write the optimizer and loss. Or you can check the solution also. Fine. Once you have defined the model and compiled it with loss and optimizer, you are ready for training. Now, train the network for 200 epochs with a batch size of 128. Okay. So, now you have to use model.fit. Then, sorry, inside that, what is the input data? X. What is the target value? Small y. Fine. Comma. Batch size. You have to just mention like this. Batch size equals to 1 to 8, comma. Epochs. Epochs equal 200. Okay. Now if I run it, see 200 epochs will, let's see. You can check here. See how loss is getting reduced. 0.348 where it has not reduced. 345, 281, 316. So the loss, not every time it will reduce, but our job that is our main aim is that it gets reduced, but every time it will not be reduced. Sometimes anyway, finally we have got 0.0269. Okay, so simply we have just created the history. Now, if you want to see that how the loss curves look like, you just plot. For that, you have to convert it the history into the data frame pd.data frame, and then you have just plot the loss. See, the loss has reduced. Then this has reduced, increased. Because see, sometimes it has increased also 0.28 to 0.272, then again increased 0.300. So like that's why it is looking like this stock market curve. Okay. Anyway, finally it has almost reached 0.0269. Okay, so every batch size was 256 or something like that, 156, and the epoch was 200. Anyway, we have got it. And you can simply plot this by keeping the history. Okay, now evaluate training. If you train the model longer, would you expect the loss to decrease further? What do you think? Not every time, but sometimes. With the learning rate and batch size, you have some control. How long it takes to train a model? Because if you give training time for very long, then obviously your time will be taken more, your space will be taken, and you have to wait, and you may not get the desired result. So always you have to think that how many times you can train so that your model gives you the best output. Okay. It depends on many things, how noisy the learning curves, how small the loss becomes. To get a better understanding of these parameters, we look at the linear model, our simplest PP simplest neural network. Only single weight and a bias, and it's easier to say how the parameter is getting changed. Okay, see. The next cell will generate an animation like the one in the tutorial. Change the value for learning rate, for batch size, num examples, how many data points, and then run the cell. Okay, see here. If I run it, let's run with their code. Here they have provided learning rate, that means at which speed it is learning, 0.05. Batch size 32, num example 256. Here you are giving the learning rate. Because sometimes what happens, see, uh, it may happen that the loss is too huge and your learning takes a big jump. So your weights shifted in a bigger way. Then again it shifts in a bigger way. So sometimes what happens, it just goes from here to there, there to here to there, and it never reaches that point. So that's why what we do, we reduce the learning rate. Whatever it has learned, we are multiplying it 0.05. So what it happens here, you're reducing the learning rate so that instead of taking a big jump, it takes a small jump. And every time it is taking a small jump and it reaches to the exact point. But if you give too small learning rate, then also there will be a problem. See, we will see it here. Then also it may not reach the point. Here the learning rate is 0.05. Now learning rate, batch size, now means number of examples. Steps 50 through underscore, that is the slope of the data, and this is the bias of the data. See, this is the fitted line. Here it is how it is changing, and this is the training loss, and this is how weights are getting changed. This is weight W, the maroon one, and this one is the bias. Okay, if you want, you just give C how it is changing. First, notice this one. This is slowly moving. If I give 1.2, now if I run it, see what happens. See here, if I have changed the learning rate, so it will never converge because it is taking big jumps. Every time it is taking big jumps, and with that it is multiplied with 1.2. So it is becoming so big that it is never getting stabilized. Weights are also like that. Training loss is not captured even. Okay, but the best is if you give 0.7. There is nothing called best. Every time you have to change, but you have to also understand that you cannot increase its learning rate or decrease it so small. If you decrease it, then what will happen? This may be an interview question. If you decrease the learning rate, then it will be so slow that it will never reach the exact point. If you increase the learning rate too much, then what will happen? Then it will become unstable. See here how it is changing, 0.7. Okay, if you give 0.2, then see what happens. This is your job. Just give this and change the batch sizes, change this, and you just check how it is looking. Anyway, learning rate and batch size. What effect did changing these parameters have? After you have thought about it, run the cell below for discussion. Okay, let's discuss. You probably saw that smaller batch sizes gave noisier weight output updates and loss curve. This is because each batch is a small sample of data, and smaller samples tend to give noisier estimates. Smaller batches can have an averaging effect through which can be beneficial. They are telling you that reduce the batch size. Then see what happens. See, when we gave 0.2, it is almost, it is behaving different. Anyway, if you give small batch size, then also you can check. They are telling you to check. Smaller batches can have an averaging effect. Smaller learning rates make the update smaller. The training takes longer to converge. Larger learning rates can speed up training but don't settle into the minimum. So when it is too large, it may fail completely. That's what we have just seen. Okay. So try setting the learning value to a larger value like 0.99 and see this. We have given 1.2 and also we have checked. Okay. So for the day, we have completed the exercise. So as of now, we have learned how to create a single neuron. So what is single neuron? How to create a stacked dense layer? How to add activation layer? How to give model? Model.compile function, how to provide the optimizer for optimizing, and how to calculate the loss. Okay, these all things we have learned as of now. In our next class, we will learn the next lesson. Till then, bye. Happy learning.